In this video, we're going to review Chapter 5, Free-Fall Gravity and Gravitation. So let's recap the last video first. If you have watched the video last week, you probably see this clip. So a man, he drops hammer and feather on the left hand side and right hand side respectively. So which one will hit the ground first? The answer must be the hammer, right? That's like the common sense. You can imagine the hammer will hit the ground first. But why is it the case? Why? Is it because heavy object fall faster or because of air resistance? To answer this question, the scientists they went to the moon and do this experiment. Okay, so they went to the moon and they dropped hammer and feather again. And what they found out is that, in fact, these two objects hit the ground at the same time on the moon. So that means, what is the reason? The reason is air resistance. So if air resistance is negligible, all objects near the Earth's surface will fall with the same acceleration. And this acceleration, we use small g to denote this acceleration. It's called the acceleration due to gravity. And this small g is approximately equal to 9.8 meter per second squared. So that means for every 1 second, the velocity of the object will increase by 9.8 meter per second. Okay, so that's why it is meter per second squared. Because per second. In the previous example, we saw hammer and feather drop to the ground, right? For any object falls under the influence of gravity only, we call this motion a free-fall motion. So, free-fall motion refers to the falling motion of an object under the influence of gravity only. So, all objects falling freely under the Earth's surface will have the same acceleration, small g, that is approximately equal to 9.8 meter per second squared, as mentioned. And in fact, free-fall motion is also a uniformly accelerated motion. Why? Do you still remember what is uniformly accelerated motion? That means our acceleration is uniform. So A is unchanged. Why A is unchanged in free-fall motion? Because in free-fall motion, A is just small g, that is 9.8 meter per second squared. Okay? In free-fall motion, we have this equation from uniformly accelerated motion, right? That is, our final velocity equals initial velocity plus a times t. Okay, and in free-fall motion, since the moment you drop this object, its velocity must be zero. That means our initial velocity must be zero. So we substitute u equals 0. Okay, we substitute u equals 0. And in free-fall motion, our a is just small g as mentioned. So we got this formula. V equals g times t. That is, our final velocity equals small g times time. So this is our equation in free-fall motion. Let's have a look on this example. A ball has been falling freely from rest for 5 seconds. What is its acceleration? B. What is its speed just before hitting the ground? The question says, let small g be 10 meter per second squared. So for simplicity, we always let g be 10 meter per second squared for most of the questions. Okay, since this ball has been falling freely, right? That means this ball is in freeform motion. Then its acceleration must be small g, and small g is 10 meters per second squared. B, its speed just before hitting the ground. We apply the equation we just learned, that is final velocity equals g times t. So small g is 10 in this question. And our time is from rest for 5 seconds, right? So that means our t will be 5. So that will be 50 meters per second. Okay, remember in part A, it asks your acceleration, right? So you have to answer the direction as well. Do you know why? Because acceleration is a vector quantity. So we care its magnitude as well as its direction. In the previous example, a ball drops to the ground, right? Let me ask you, why the ball dropped on the ground? What is the reason? You probably may say, oh, because of gravity. When you think of gravity, you must think of Newton, right? So what is gravity indeed? Gravity is actually a force that attracts a body towards the center of the earth. So all the things on the earth, like balloon, me, so we all are attracted by the earth. Okay, and this force is what we call gravity. However, Newton thinks further than us. Newton thinks Earth is just like a big rock, right? It's just like a big rock. It is a big rock. So, if a big rock has such attraction, then so does a small rock attract other objects as well? So, in 1687, Newton developed the idea of universal gravitation. This law says, for any two objects of mass m1 and m2, separated by a distant r, the gravitational force between them has a magnitude of F equals big G times m1 times m2 over r squared. Okay, so this is like a difficult formula. So what is big G? First, big G is the gravitational constant. Okay, and this big G is approximately equal to 6.67 times 10 to the power of negative 11. Okay, this units. So this is a constant. Okay, and m1, m2 is just the mass of two objects. Okay, and r is the distance between two objects. So simply speaking, if we have two objects, okay, we have mass m1, mass m2. Then these two objects, they will attract by each other. F1, F2. And this force is what we call gravitational force. So, and the magnitude of this force is equal to big G times m1 times m2 over r squared. Does it make sense? You may probably say, it doesn't make sense. Like, suppose I have mass, my mass is maybe like 50 something kilogram, your mass is 50 something kilogram. But do we attract each other? When I first learned this law, I think, okay, it's just weird. If every object just exert a gravitational force on each other, why don't we stick together? You just said, okay, you just say we have this force that sticks us together, but we won't. Why is that the case? Let us do this example, then we will know what is the reason. Harry and Rainbow both have mass of 50 kilograms. Find the magnitude of gravitational force between Harry and Rainbow when we are 1 meter apart. B. Between Harry and the Earth. Okay, so we have got the mass of the Earth and the radius of the Earth. So first, the gravitational force between Harry and Rainbow. So big G is a constant. We just substitute the number. Okay, M1, the mass of Harry. M2, the mass of Rainbow. So we substitute. Okay, and this R is the distance between Harry and Rainbow. It's 1 meter. Okay, so all the things take into account, then we get the result. 1.67 times 10 to the power of negative 7 Newton. B. Gravitational force between Harry and the Earth. So big G is still constant. Okay, just some number. M1, the mass of Harry. M2, mass of the Earth. We just substitute. Okay, and this R is the distance between Harry and the Earth. So which is the radius of the Earth. We just substitute there. Then the result would be 491. So now, do you understand why we won't attract by each other? What is the reason? Because, simply speaking, this force is too small, right, to stick it together. So that's why it seems like it is not true, but this is the true case. But now, I've got a new question to you. If the mass of the Earth and the Moon is so large, then why doesn't the Moon fall to the Earth? And doesn't the Earth fall on the Sun? They should have a very big gravitational force on each other, right? Because the two masses are very large. Why is that the case? Could you make a search and tell me later?